Okay, this presentation is going to be about astronomical observing tools, such as telescopes, mounts, different types of telescopes, different types of mounts, etc. I'm from, of course, the Denver Astronomical Society. My name is Steve Barr, and I put the date down there also just in case somebody has to set their watch. Tonight's agenda will just go a little bit into visual observing, just to recap, essentially a review of what Mehmet talked about last week. A very brief review, I might add. The other thing we're going to talk about is I put this together. I started talking about telescopes and nothing seemed comfortable unless I included somewhat of the history. So that'll be the next thing we talk about. A little bit about characteristics of telescopes, focal length, aperture, etc. Talk a little bit about binoculars briefly, go into the basic telescopes types, primarily refracting and reflecting, accessories, mounts, reference materials, and we'll close it up with some questions. Okay, this is of course by the Denver Astronomical Society, supported by the Secular Hub. Just an overview of astronomical tools. There's no need to own either a scope or binoculars or any type of observing material, actually, or equipment. To be an astronomer, all you have to do is have an interest. If you have an interest in astronomy, I consider you an astronomer. As a matter of fact, from my perspective, I probably enjoy just studying about astronomy because there's so many fascinating things out there to read about and to ponder. And as a matter of fact, I can know of at least 2 cases where people who have been blind from birth are astronomers. And one of them, as a matter of fact, took radio signals and somehow or another she turned them into noise, and as a result she can actually identify something just from the noise, from the radio signals, which is a pretty darn amazing thing, I think. We're going to try and keep things at a basic level. But however, if anybody has any questions about anything, you are free to interrupt me at any time. So, any questions so far? About me, I am not nearly so colorful as Mehmet's introduction was last week. I am just a retired software and systems engineer. I worked in the aerospace industry. And the limit of this is something that I'm quite proud of, quite honestly. The limit of my actual verifiable astronomy credentials is a Boy Scout merit badge when I was about 11 years old. I will justify that by saying I did teach the counselor a few things. Currently, I'm a DAS outreach coordinator and a DAS trustee. My hobbies, music, reading, and I like adventure sports, particularly adventure sports, which takes me into the mountains. And this is my better half. Little guy by the name of Tatters. He was taking me for a walk in Castlewood Canyon at this point. Okay, visual astronomy. Our eyes are the most economical way to study astronomy. People have been doing it for thousands of years. Herders, shepherds, just wanderers, they gazed in amazement at the night sky. And as a result of that, they saw things that moved. They didn't really know why they moved, but however, they called them wanderers. And the Greek translation for that is planets. So we have planets now today. And we have many, many myths that are associated with all the constellations, that they connected the dots around there. And as I look at things, I know that somebody had a great deal more imagination than I did. And this is just, of course, everybody can probably find the Big Dipper after the presentation last week. Has anybody seen the Big Dipper? Okay, a few people have. Very good. Okay, and as a result of seeing the Big Dipper, using Merak and Duba to point to Polaris, and that is your first orientation point. And also, one of my favorites is using Cassiopeia, which is just the W. And I think that many, many years ago, actually this star right there was connected. So it looked more like a chair than a queen, actually. But however, if you use that star and a star called Shedar, it will point you to the Andromeda Galaxy, which will, for the naked eye, it will look like a fuzzy patch in dark skies. If you, you're going to need a little bit more than that if you live in Denver. And here we go, as I promised, the history of observing tools. Some of the first actual instruments were invented and used by a guy by the name of Tycho Brahe. And what it was used for was to measure the positions of the stars, planets, etc. in the sky. And that was actually the first time anybody really took such measurements that I know of anyway. Might have been other very rough measurements, but however, and he did it with a great deal of precision also. If we take your little finger and you hold it up, and your fingernail would just about cover the full moon or the sun for that matter, which is, from our perspective, just about the same size, although one is probably about 400 times bigger. But however, if you think about the accuracy that was approximately around the order of 30 seconds, if we think about the moon, which is 30 minutes wide, okay, and each one of those minutes are divided up, so you're talking about essentially about 1/60th of the diameter of the moon. That was the accuracy that he had with these instruments. And later, these measurements were used extensively by Johannes Kepler. Johannes Kepler, of course, he formulated the three laws of planetary motion, which was a great thing. And for some reason that I have never really understood, Brahe kept those measurements away from Kepler until he died. But however, Kepler made very good use of them and did some really amazing work. As a matter of fact, in my opinion anyway, if I had to pick anybody in history that was comparable to Einstein, I think it would be Kepler. Refracting telescopes was the first thing that we had. Back in around 1609, actually, a Dutch mathematician and astronomer by the name of Hans Lippershey developed the refracting telescope, the first refracting telescope. It was just essentially a long tube with a lens on both ends. And then actually what you can do, does anybody have magnifying glasses at home? Okay, what you need is, if you have a big magnifying glass and a small magnifying glass, what you can do, and one of our outreach volunteers, sometimes he will bring big magnifying glass and small ones, and you can actually, if you get them positioned just right, you can actually magnify something in a distance. And I have seen people say that they can actually do it. I've never been able to do it, but nonetheless. As a result of that, Galileo developed his own around 1610. It was long before the days that we could order things on Amazon, for instance. Okay, he discovered sunspots, Venus phases, Jupiter's moons, and moon features. Of course, eventually Galileo went blind, but however, it was not the result of looking at the sun. As some people have speculated, he actually projected the sun, and that's how he found sunspots. So he did go blind, but however, it was just the result of older ages, I guess. And his telescope was actually about 3 feet long and a power of about 30x. You know, we have binoculars that are just as powerful and much, much better optics now. It produced an upright image. As a result, there was no intermediate point. The light came in the front end and went back, and the focal point was actually back here. We had a little eye relief. In other words, you had to get very close to be able to see anything. But then Kepler, another one of my favorites that he did, he improved on the design by changing this rear lens, extending the focal length, and had a focal point here. But what happened as a result of the focal point being there, the intermediate focal point, we'll call it, the image was inverted rather than upright. And also it had greater eye relief. And binoculars or field glasses. It didn't take people long after the invention of the refracting telescope to start thinking about, gee whiz, if I can put two of these together. But it was somewhat of a more difficult job than what they expected initially. It will give you somewhat of a three-dimensional image as a result of parallax. Everybody's familiar with parallax? Stick your finger in front of you, close one eye and then the other, and it appears to move across the screen, across the background. That is essentially parallax. Very, very important in the study of astronomy. Various designs were introduced after the invention of refractors, but however, it was about 1820 before anything was really useful. And as a matter of fact, like these guys right here, the first use for binoculars, believe it or not, was as opera glasses. And this is a much more modern version of it here. And also reflecting telescopes. The first ones was actually built by Newton back in 1668. And if you can imagine, those of you who have reflecting telescopes, what it's like to only have a primary mirror probably about that big, maybe a little bit smaller than that even. And the difficulty it must have been trying to grind and work on something that small. Unfortunately, Newton's first telescope is lost to history somewhere. I think he lent it to somebody in England, never saw it again. This telescope was, I think, his second one. Well, it's a replica of his second one. I'm not sure that his second one has even survived. The big thing about the reflecting telescope, it was to eliminate refractor chromatic aberration. Okay, we'll talk about that in a moment also. Led to various popular designs, including the Cassegrain, SCT, MCT, and the RC type of reflecting telescope. And we're going to talk a little bit more about these later. But however, here we have examples of a Newtonian reflector, and this is a Cassegrainian reflector, and also this radio dish is actually a Cassegrain also, because everything comes in here and bounces up onto the feed and then down. Okay, and I think that's about. Anybody have any questions on the history? Okay, aperture, talk about some characteristics that's common in all telescopes. The aperture is just the diameter of the lens or the primary mirror. For instance, this happens to be an MCT. We'll talk about that in a moment, but however, it is a reflecting telescope. It has a 90 millimeter mirror back here. Thus the aperture is 90 millimeters. Okay, the greater diameter, more light gathering capacity. And the focal length is just the length between the aperture and where the image focuses. Okay, longer focal length means greater magnification, however, a narrower field of view. Likewise, a shorter focal length is less magnification, but a wider field of view. I might add that the shorter focal length will give you more contrast as a result. If you're looking at some faint objects, it's a little bit easier to see with less magnification and a short focal length. Likewise, the F ratio of a telescope is just the focal length divided by the aperture. For instance, if we have a focal length of... Yes. What? I'm going a little fast. Okay, I can slow things down. Okay. Any questions about aperture or focal length? You okay there? You're welcome. Also, we have the F ratio, which is just the value, take the focal length and divide it by the aperture. So if we have a focal length of 400, we'll say, and a aperture of 40 millimeters, anybody want to guess what the F ratio would be? 40 by 10. Okay. Lower F ratio means greater light gathering. Faster optics. Faster optics is very important in astrophotography because you don't have to, when we say faster, you don't have to spend as much time taking a picture. And the higher F ratio, we have less light gathering capacity. Slower optics, less contrast, okay, as was alluded to previously. Okay, we have the eyepiece focal length, which magnifies the image at the focal point, and the magnification, which is the focal point, focal length divided by the eyepiece focal length. Okay, so another quiz that I'll have for you. If we have a focal length of 400 again and an eyepiece that is 10 millimeters, okay, what is going to be the magnification? Right you are. Okay. Everybody clear on that? Binoculars and astronomy. The great way to get familiar with the night sky. That's one thing I will say about binoculars. I don't use binoculars very much. Never got very good at them. But however, I do have a set that's almost identical to those. So 25 by 70, I think they are identical. Binoculars, it's a little bit more economical way to get into things. If you have even a pair of 10 by 50 binoculars, you'll probably be able to bring out things such as Jupiter's moons, for instance, because they're only about sixth magnitude. I'm not sure that you'd be able to see Saturn's rings, but if you have sharp eyes, it's entirely possible. Binoculars are basically pretty darn clear also. So they're easy to use, ideal for beginners. And it's nice to just go out and lay down on a recliner and look up the sky and put the binoculars and just scan around the sky. From my perspective, what happens, occasionally I do that with my binoculars, and I see some pretty darn neat things. I don't really know what I'm looking at, but nonetheless, I see quite a few different interesting things. I might be able, if I'm very lucky, I might be able to nail it down to a quadrant. That's about it.
So these are 12 by 50.
Yep. 12. 12, that's, yep. So actually the 20 is the 50 is the field of view. So if we take, what would be that? 15, I think you'd be f4 on the binoculars, which is pretty darn fast. You should be able to see some pretty interesting things with those. So, okay. Binocular types, there are only two types of binoculars, and they're developed with prisms, something called a roof prism, which essentially it comes in and straight through. Actually, as said previously, two refracting telescopes put together. And they're easy to handle. They have a narrower field of view because the objectives are not as far apart as these. And they also won't give you as good of a 3D effect. Or the poro prism, which is the ones that you have right there. Do you want to stand up and look? Let everybody see. Hey, those actually are roof prisms. Yeah, okay. Because you see, you don't have everything straight through. As right here, light comes in straight through and through the eyepiece. The only thing also about binoculars, it's not really a good thing to share for the big reason they have to be adjusted for your eyes, for somebody's specific eyes, and if you pass it to somebody else, they have to be readjusted, so you are free to be stingy with your binoculars. Different types of binocular mounts. Even one of the reasons why I mentioned just get a recliner and lay back, that is the best way that I have found to use binoculars, because if you stand up and even just look for any amount of time, it does tax your arms somewhat. There's no question about that. So, that works too. I still like laying down. I'm a little bit lazy. Okay. And we have, there's different types of mounts, essentially tripods. You can even mount binoculars on equatorial mounts so they can track. But however, usually people do not bother too much with that if they're going to go to all that trouble, they're going to use a telescope. So, but all kinds, we have just the basic tripod. We also have, this is called a scissors mount. That was it, yeah. And binocular targets, probably some of the favorite ones are the things we can just see with our naked eyes. The moon, the planets, possibly even the Andromeda galaxy. Do not try to look at the sun with binoculars unless you have white filters on them. That is one of the things that anytime we have a outreach event in the daytime and we're looking at sun, we have the same guy that brings the magnifying glass always brings a bunch of ping pong balls with eyes painted on it. And he will hold the ping pong ball up to the telescope the eyepiece, and of course it incinerates pretty darn quickly. So that is a good enough reason not to try to look at the sun. We have three types of popular astronomical telescopes. The one, of course, is the Refractor. Another one's the Newtonian. And the other one is the Schmidt-Cassegrain. We will talk about the light paths and everything and a little bit later. And these things are called catadioptric. Anything that uses both lenses and a mirror. I always loved that word, catadioptric. I can remember, just as if anybody wants to hear a little bit of trivia. Okay. We used to have a game that we called Probe, and you could make words out of it, and you always put what the letters were face down, and people tried to guess it, what it was. And back in my teen years, I always liked to use the word catadioptric because it had 12 letters that filled the entire board up, and nobody could guess what it is. And everybody said I cheated, and they challenged me that it wasn't a word, but they found out then that it was. The only thing is, I only ever got away with it one time. Refracting telescopes, both the Galilean and the Kepler telescopes had a problem. The problem is called chromatic aberration. If we look here, what we have, the light coming through, and this is the focal point for all of these types of light: red light, green light, and blue light. If you'll notice, nothing focuses at the same point. This, of course, would create a problem because if you want to look at blue light, depending upon the object, you would have to change the focus, as opposed to if you wanted to look at red light. But we ended up with some very smart people back in even the 18th century that came up with the idea of an achromatic refractor. Achromatic refractor, it's supported shorter focal lengths, and it used two types of glass, crown and flint glass. I hope nobody asks me what the difference between crown and flint glass is, because I can't answer that. Okay, we reduce the chromatic aberration by bringing, note, the red and the blue together. The green was still a little bit out of focus, but as a result of that, and some enhancements made by a guy by the name of Joseph Fraunhofer, who was one of the great astronomers in history. He was responsible for helping to develop the achromatic refractors. Also, he did some of the first work on the spectrums of the sun, and a German equatorial mount, which you can see right here. That was his invention way back in the 1800s. And as a result of everything that happened, achromatic refractors, some of the great refractors of the 1800s were born. As a matter of fact, the telescope at Chamberlain, 20-inch telescope, I believe at the time, was it the fifth largest in the 1800s, the fifth largest refractor? Because I can't remember. First was Yerkes, next was Lick, and I think the 20-inch was number 5. I'm not sure about that. Why don't somebody look that up for me? Okay, and any questions on that so far? As far as that goes, both the achromatic refractors are still used quite a bit, and they're sold quite a bit there. They're called doublets. more so than anything else. If you see something that they say it has an ED lens, for instance, that's going to be an achromatic. And we ended up with a further development by adding, believe it or not, another lens. We ended up with something called the apochromatic refractor. It had three elements in the objective lens. It was first built in the 1800s, but however not very popular as a result of the cost and the labor involved in developing it. But however, what it did do, it brought all three, red, green, and blue, light together. But however, the APOs, by the time they got to be economical to make, reflecting telescopes had taken over. But however, the aprochromatics was also a boom for the current astrophotographers because they have a much clearer view and everything is in focus. Some other types of refracting telescopes, we have quadruplet, quintuplet, and Petzl designs. If you're just a beginner, I wouldn't worry too much about these, and especially if you're not planning on doing astrophotography, it's probably not a good idea either. So, and most are specifically astrographs. Not very good for visual whatsoever. As a matter of fact, I have a telescope that it is a Petzl, and I have tried to dispute that, and I have never had any luck using it visually, but however, it is a great photography scope. It's these are much more expensive than APOs of the same size, although normally any of these quadruplet, quintuplet, or Petzls, they normally come, I don't know that I've ever seen them in any bigger than 100 millimeter objective. And this is the Petzl design down below, which essentially is just two doublets, one, and then they turn one around, and everything comes to a very sharp focal point. I have a Petzl, and yes, for photography, I'm very well pleased with it. Refractors, the bottom line. Achromatic, it's great for visual observing. Okay. The worst thing you're going to see is some possible chromatic aberration around the edges. And as technology changes, there are many of the EDs or achromatic that can compete with the APOs as far as clarity goes. And APOs are actually clearer and better for astrophotography, but however, they're also more expensive. If I had to take a wild guess, if you're going to pay, I don't know, $1,000 for an ED, you're going to probably pay at least half as much again. Yes, Dina?
Ninth largest in the USA.
What? Well, Chamberlain, that's an ED.
You were asking if it was one of the largest telescopes?
Oh, yeah.
Ninth largest in the nation.
Okay. For refractors?
Yes.
Okay. So I was wrong. Okay. I'm not going to admit that very often. Okay.
Telescope you get at the warehouse?
What was that again?
What kind of telescope do you get at the warehouse?
What kind of, at a
Costco
Costco or
or something?
something, I wouldn't do that. To tell you the truth, you can see one of the things that I really think is actually false advertising. If you see a box with an astronomical telescope inside of it, and it will show on the box, it has these beautiful pictures of nebula and galaxies and everything that is just not reality for that telescope. For one thing, what you're going to see as a result of the Earth's atmosphere, most everything's going to come through, especially deep sky objects. You'll be able to see a little bit of color in, such as the Lagoon or the Orion Nebula. But however, they end up being primarily faint fuzzies. And that is why I think that seems to be somewhat false advertising to have those pictures on the front of those boxes, because it's deceptive. So as a matter of fact, if you, and the bigger aperture you have, you can bring up those colors much, much better. Such as, for instance, a good friend of mine lives about a mile away from me, has a 22-inch Dobsonian telescope, which does a pretty good job of bringing some of the colors out, such as the Lagoon or the Orion Nebula. But, however, most people will find a 22-inch Dobsonian a little bit unwieldy. So
it's pretty wide.
yep, 22 inches, the primary mirror would be 22 inches. Mm-hmm. So he uses it just for most realistic purposes for visual observing, but however, he has got into it with something called electronically assisted astronomy, where you actually hook a camera up to it and take pictures, because he said his eyesight's getting a little bit bad, and that will help him see some things a little bit clearer. And I'm getting a little bit off the subject, but however, he has seen things such as I have seen some of his pictures, and he has taken pictures of the the Hickson galaxy clusters or the Abels galaxy clusters, which are pretty faint objects. So, okay, where were we now? APOs, okay, they are more expensive. They're still great for visual. You'll get a little bit of coma around the edges, which can be mitigated by using a field flattener. And other designs, I wouldn't bother about it unless you get a little bit more experience and you get into astrophotography. So, and for astrophotography, I can't stress enough trying to start out small, at no bigger than 100 millimeter objective lens, and with an APO also, rather than a reflector. We have popular reflecting telescopes. We have the Newtonian reflector, which we talked about, Cassegrain, the Schmidt Cassegrain, and the Maksutov Cassegrain, which that is what this little guy is. And both of these use both lenses and mirrors. As a result, they're known as that, one of my favorite words again, catadioptric. We have on the Newtonian reflecting telescopes, the primary mirror was less than 2 inches, as we said previously. Mirrors instead of lenses, Newton's idea was this would eliminate the chromatic aberration found in refractors, and it did a pretty good job of that. It's a simple design. It's very popular with amateur telescope makers. If you ever see anything, the acronym ATM, and it's talking about astronomy, that's going to be normally amateur telescope makers. Everybody caught up on that. The Newtonian reflecting telescope, the advantages, free of chromatic aberration, and the big thing really is it's less expensive, gives the biggest bang for the buck. In other words, it's a very popular for beginners and as simple as out mounts, The only thing about them is you would have to continually adjust them as things continually drip out of view. And easy to make a shorter focal length, thus wider field of view, and I might add a little bit more contrast also. It's easy for adults to view, and a variety of different types of mounts can be used. This is a type of an equatorial mount that is on this Newtonian. Disadvantages is we have something called coma. Anybody know what coma is in a telescope? If you look on the outer edges and you see these little comet-like things, okay, they almost look like teardrops. That is coma. You'll see a little bit of that in the Newtonians. That can be corrected though. And also the secondary mirror, which would be right in here, it obscures a little bit of light. So if you have an 8-inch aperture on a Newtonian or any reflecting telescope, you're going to actually have a little bit less than that, depending upon the size of the secondary mirror. Okay, the spider that holds the secondary mirror is essentially just a cross, like this, and what that does, it makes diffraction spikes. Some people love diffraction spikes. They just think that it makes the stars, for instance, a little bit more attractive. You can be your own judge of that. So, as a matter of fact, I believe, if we look over here, for instance, right there, that is a diffraction spike. So we know that this picture was taken with what? Newtonian, you're right, you passed the class. Okay.
It seems like you see a lot of that with James Webb.
Yeah. What was that?
It seems like you see that, a lot of that effect with James Webb.
It's different though with James Webb. The reason why you actually do not see 4, you will see 4 on the Hubble because it has the spiders, just like the Newtonian does, or the classical Cassegrain. The reason why they have that and they don't have UC6 is because the mirrors are divided up and all the mirrors are hexagonal, and that is what creates the 6 diffraction spikes. Everybody clear on that? Okay. Collimation can be a problem with in other words, what you have to do with actually just about any reflecting telescope, you have to make sure that the secondary mirror is lined up with the primary mirror. And so there are these knobs that you fiddle with back and forth, and it gets to be a pain, but I will have to admit that I have a 10-inch Newtonian reflector at home that I use just about exclusively for astrophotography. But I'll have to admit that I would use it a whole lot more if it was a little bit easier to collimate. Okay. And lastly, since I'm involved in outreach, one of the things that I have found is that the eyepiece can be too high for little people. So, Cassegrain reflecting telescopes. For this presentation, I looked into the history of these, and it's a little bit fuzzy, but the design is attributed to a guy by the name of Laurent Cassegrain in 1672, only about, 60 years after Hans Lippershey developed the refractor. Okay, and this uses a parabolic mirror and a hyperparabolic secondary mirror. Okay, parabolic means the primary mirror is shaped in a parabola, and likewise the hyperbolic secondary mirror means it's shaped in a hyperbola. Okay, mathematically those are two different things. Okay, I like the Newtonian. It's free of chromatic aberration, free of coma. There are several variations, with the most popular being the Ritchie-Crichton. The Ritchie-Crichtons is actually the design of both the Hubble Space Telescope and the James Webb Space Telescope. Okay, and the big difference with the Ritchie-Crichton, both of the mirrors are shaped like a hyperbola rather than one and then the other, rather than a hyperbola and a parabola. Cassegrain reflecting telescopes, we have high magnification with them because of the focal length being longer. We have a short optical tube. They're a little bit easier to handle, clear image, and they are great for deep sky photography in particular. Disadvantage is it's more difficult to build, more expensive, diagonal required for visual. In other words, back here at the end, since the light is coming out and then coming back, you would end up sort of with a neck-breaking scenario if you got down and you looked at it. It's a lot easier just to look down into an eyepiece. Okay, and there's a central obstruction, cuts out a little bit of the light, but however, not much. And they are very difficult to collimate from what I hear. This is one type of telescope that I don't have that I've always wanted, but however, being that I have enough trouble trying to collimate a Newtonian, I don't know that I don't know that if I want to tackle a Cassegrain yet. And then the catadioptric telescopes, optical systems using both lenses and mirrors. Like catoptrics means curved mirrors, and dioptrics means lenses. Okay, and in both of these cases, what we have a lens here, and we have a mirror, two mirrors actually. And what that does, it gives you a great deal more focal length. The only problem is, in particular with the SCT, it would be much, much heavier. It's more aberration-free than Newtonians and refractors, and they have a holding light path. Thus, it's a more compact design, but however, it's also much harder to manage and much harder to lift around and mount on your equatorial mount. Schmidt-Cassegrainian was developed by a guy by the name of Bernhard Schmidt in 1931, and spent quite a bit of time developing this lens right there. And what the rumor is the way he developed it, he just laid a flat piece of glass down, and he tied a weight to the bottom of it so it would pull it down, and then he just filed it off until it was smooth. And that was the start of the SCTs. And also the MCTs, the massive Cassegrainian, was developed not all that long afterward by a Russian by the name of Dmitry Masutov. I've always had a problem with that word. So, but however, note, it's a little bit curved, just like this telescope. This is actually a Masutov, but that gives it a great deal more focal length for the size, such as this little telescope right here has a focal length of 1200 millimeters. I have a 10-inch Newtonian that I talked about previously that has a 10-inch mirror. It's about that big. It only has a focal length of 1000. So you get a lot more. That makes these a lot better for probably planetary objects or the moon. Catadioptric telescopes, we have advantages. We have a compact design, easy to store and transport. such as a telescope like that, an SCT, will probably have a focal length of around, probably well over 2,000. More aberration-free than other scopes. And the MCT has more aberration than an SCT, but however, the MCT has the most focal length for the size. If we look at these two telescopes right here, we have an SCT and probably a much smaller MCT, which is probably just about the same focal length, but however, it doesn't have anywhere near the light gathering capacity of the SCT. And the disadvantages, the SCT, as we said, it's going to be quite heavy. It's hard to make the corrector plate of an SCT or meniscus plate of the MCT, and it's also expensive. Okay, they call that a meniscus plate. Anybody take chemistry in high school or college? And if you put water in a test tube, and you'll note that it's a little bit curved, that is a meniscus. And so that's, I presume, where that term came from. The SCT and the MCT are very popular designs for the catadioptrics. My optical device conclusions, and this is, again, a little bit of my own opinion, so you can take that for what it's worth. What are you going to use it for? Is it just going to be private use? Is it going to be outreach? Sidewalk astronomy? Are you going to set it up in the middle of just on a sidewalk and let people look through it? Or are you going to be interested in just planets, the moon, the sun, etc.? Or are you interested in galaxies, globular clusters, open clusters, nebula, and so forth? What is your budget? And is a refractor better than a reflector? That is a question that people ask me occasionally, and I say yes, it is. It's clearer image, a wider field of view, and better for brighter optics. And then they ask me, is a reflector better than a refractor? And likewise, I say yes. We have a larger aperture for deep sky, greater magnification, and the big thing is that the Newtonian is going to give you the biggest bang for the buck. And I know I might have scared a few people away as a result of my own travels and my difficulties I've had with collimation, but however, with the smaller mirrors that you have with the Newtonians, they rarely ever need to be collimated. Back probably I was 5 or 6 years old, and my astronomy ventures started with my dad's 20-power spotting scope. I just went out there, and of course we didn't have access to the web at that point, so I just had to look at one star after another. And I can still remember the first time that I actually nailed Jupiter. I was so excited. Some of the accessories that we can have to eliminate the sharpness around the edges for refractors, we have field flatteners, and coma, we talked about that, what's stars that look like coma around the edges. We have coma correctors, okay, similar to field flatteners, but reduces coma in Newtonian specifically. Okay, we have focal reducers and field flatteners, a combination of them. If we want to know what a focal reducer will actually improve the sharpness around the edge, and it reduces the focal length also. So if you have if you have a refractor with a 500 millimeter focal length, what happens if you put a 0.8 field flattener on it? You end up with only 400. So as a result, you end up with a wider field of view also. But however, Both of these are probably only necessary for astrophotography. Likewise, diagonals, this is a must for refractors or the Cassegrain, the scopes to avoid neck breaking, we'll call it. Barlow lenses, we increase the focal length from 2 to 5x. In other words, you can, 1000 with the 2x Barlow, you can increase the focal length of a 1000 millimeter refractor up to 2000. Greatly increases the magnifying power. It also decreases the field of view, and from what I have seen, things are not quite so clear. You don't have the contrast also. But however, they are great for planetary photography, very questionable for visual. One of the things the Barlow will do, though, if you use the Barlow and one of your lenses, essentially it makes turns your one lens into two lenses. So such as it would turn a 10 millimeter lens into effectively a 5 millimeter lens with a 2x Barlow. Okay, and I think that eyepieces, you may have lots of these if you want to follow this hobby to any extent, and you want to use these for personal or public viewing. For instance, I like to use my best eyepieces. I'm probably a little bit more stingy with them. And so at outreach events, I end up using these things, just these super Plossl, and the more expensive ones, actually I do use them sometimes, but not very often in outreach. And you can pay whatever you want to from them, anywhere between, like I said, probably $25 to $1,800. $30 there, $100, almost $900, and the winner is this guy over here for $1,600, which actually not only is an eyepiece, it's a camera also. Okay, everybody clear on that? Oh, you like that one? I'm going to have to use that more often. Okay, we have finder scopes, cross-haired sighting device used to bring the target into the field of view of the primary telescope, and both of those optical axes, both for the primary and the guide scope, should be aligned so they do line up when you look through the main scope. It's a little bit of practice, but however, it's not all that hard. What I recommend instead of a finder scope is something called a telrad, which is right here, and that is what you see through a telrad. As a matter of fact, I have a telrad right here that I'm going to pass around so people can take a look at it. I don't think that it'll be fine, and so you can see through infinity. There is no magnification on it, but however, it is divided up into half degree, 1 degree, well, that's a half degree circle, 2 degree, and 4 degrees. So I'm just gonna, if you'll excuse me for a minute. It is dark enough in here. You want to pass that around? Take a look through there. That is what you're going to see through a telrad. Nope, just look straight through the end of it. There are 2 AA cells. Mm-hmm.
And this, when you've got your big scope, this is like where.
What you want to do with the big scope, you want to have the optical axis of this lined up with the big scope. And what the nice thing about this is, it's very, very easy to adjust. There are 3 knobs here. This one will move the crosshairs up and down, and these 2 will move it at a diagonal. So about all you have to do is just get something just about straight up and down, and move these 2 until something is straight up and down, and then this to adjust the elevation on it. Okay, but yeah, can you see the?
Yes, yeah, the red thing, yeah.
Yeah, the red.
Yeah, that's cool.
Much easier to use than a finder scope. And the big thing is it's much easier to adjust also than a finder scope, because with the finder scope, you have all these at least 3 and sometimes 6 of those little knobs to adjust, and it gets to be confusing, quite honestly. Another thing, one of the accessories that we have are guide scopes, but however, probably only necessary if you're doing astrophotography. Okay, we've been at this for about an hour. Does anybody want to take a little break? Oh, okay.
So you've got the primary and secondary mirrors,
The primary,
secondary here.
yeah.
They face each other. How does that get image come out so that you can see it? If they're reflecting to each other, how do you see it?
Because what happens, I'm going to have to feel. Okay. What happens? You note the light comes in, goes through the corrector plate.
What is a collector plate?
This is actually, I'm looking at an MCT right there, so it's actually called a meniscus plate. Okay, but however, with the SCT, the light comes in and it bounces off the primary mirror and back to the secondary mirror, and then it comes out to the focal point.
So there's that hole there, but previous illustrations don't show that gap. It just shows 2 mirrors facing each other.
Yeah, I don't know if I understand.
Well, you have 2 solid discs versus like some kind of gap there.
The gap for the,
So if you go back to a previous example, even previous to that, yeah, like that.
yeah,
So I don't see where the image comes back to you. It's supposed to-
the image is right there at the focal point.
Is that what you see?
That is what you see. Actually, that is what the eyepiece, that is what the eyepiece magnifies. The eyepiece is actually magnifying the image that is at the focal point.
So F is the eyepiece.
After the eyepiece,
Letter F is the eyepiece. That's where our eyeballs look through.
yeah, that is something that you might call the eye relief. Okay, and that would be some place on the other side of the lens, of the eyepiece lens, such as, for instance, as we talked about Galileo scope, you had to have your eye very close. Okay, it didn't give you what you call eye relief, but however, what you would, but the Kepler scope, it gave you much more eye relief. So in other words, it was actually easier to look through. You can move your head away a little bit anyway. I'm not talking about a significant amount. I'm talking about probably half inch to an inch. I never used any of Kepler's scopes, so I don't know. I don't know for sure.
One thing I've always wondered, so the focal point is just for one eye.
You want to give people 10 minutes? And
Yeah, 10 minutes is fine. And I will answer any other questions that I can answer.
10-minute break.
Everybody here? All right, we'll talk a little bit about telescope mounts. I'm probably going to try and cover this in about 15 minutes. Just an alt-az mount is just a simple two-axis mount moving the instrument in a perpendicular axis. In other words, it's just moving it back and forth, what we'll call the azimuth, and then the elevation, which is up and down. That would include the Dobsonian mounts, fork mounts, and just about any tripod-mounted camera. Or we have equatorial mounts, which would be a fork mount with a wedge on it, or the German equatorial mounts. Dobsonian mounts, they are very simple, they're very easy to use. You can just take them out of the box, and again, you want to get the finder scope aligned with the axis of the primary scope. The only thing about them is they will require constant adjustments. They're quick and easy to set up, and they're also cheap. Probably any type of a mount like this with even a 4 or 5 inch Newtonian reflector would be ideal for a beginner. The automated ones, it's a longer setup time, they're more expensive, and they have a trouble tracking if you're very close to zenith, which is straight up. Okay, field rotation is going to be a problem when you're photographing. Since you're not moving along an equatorial axis, what happens is the actual image will shift around the edges. If you're taking very short exposures for photography, probably won't matter, but however, it's going to be a problem with a longer exposure. And we have alt-az fork mounts. Any of the ones that I've ever seen are all automated. They're cheaper and easier than a German equatorial mount of the same class. Easy and convenient from celestial to terrestrial. So you can do your bird watching in the daytime with a fork mount and then look at whatever you want to in the night sky. Okay, and the alt-az mount, or the fork mounts, it becomes an equatorial mount if you install a wedge, which is just essentially something that goes on the tripod, but however, it lifts the one edge of this plate up so you can track as you do with a gem. Disadvantages of this is, in particular with the SCT, is the weight, because this is all one unit and it has to be carried. They can be quite heavy, even from 8 inches up. Unless 8 inches up, they can be very heavy. We have field rotation, as is the case with the Dobsonians. And with a true fork mount, you can't switch scopes. Things come mounted in there. I one time had a 10-inch Meade mounted in a fork mount, and eventually I ended up taking it out. For one reason, the fork mount quit working, and I like a mount that you can switch scopes. These things right here that I call the one-arm bandits, they actually do have a dovetail directly behind here, which you can use to switch scopes. In other words, you could take that, whatever that is, a 6 or an 8-inch celestron scope out, and you could put a refractor in it. Okay, everybody okay now? And we'll go proceed. Come on, be patient, okay. And we have a German equatorial mount. and developed by Joseph von Fraunhofer, whom I mentioned several times before. All you have to do is set the latitude, polar alignment, and steer to a declination and a right ascension. It will usually require a counterweight if you have a scope of any size, but for instance, this scope that I have right here is, I'll just carry that out a little bit. It's light enough for me to carry. This is German equatorial mount. And all you have to do is, first off, you can adjust the elevation for your latitude, such as we're about 39 degrees right here. Adjust this to 39 degrees, or what I prefer to do actually is look at the North Star and adjust according to that. Okay, and then after you are polar aligned, what the scope will do, see, it just moves in a circle. Okay, in other words, and if you're very well polar aligned, what will happen if you have an eyepiece with a reticule in it, you will see the North Star just go around in an even circle around the central point, because the North Star actually isn't pointing due north. It's something to the order of 0.86 degrees. Bring it up here. Thank you very much. Everybody see the TELRAD? You didn't? Pass that back. Oh, you're going to be amazed. And then this is just everything, actually just, if we look north, everything revolves in a big circle. Right now, it's revolving in a very small circle, but however, if I change the declination like here, it revolves in a much bigger circle where it's pointing. Okay, and likewise, you can move it a little bit more, and it moves in a bigger and bigger circle. And that's essentially what all of the German equatorial mounts do. Any other questions about a German Yes?
I have a question on the Alpaz. How can you do photography with an Alpaz mount? If I find you can only do it with an equatorial.
You can do it with an Alt-Az mount, but however, the exposures have to be relatively short, because you'll get field rotation otherwise. Okay, such as, for instance, my friend that I told you that had the 22-inch Dob that is working right now on doing electronic assisted astronomy. He is taking relatively short exposures and stacking them, and he's come up with some pretty good results. And he has a big advantage since he has a 22-inch mirror that has a great deal of light gathering capacity. Okay, he can take very short exposures, and probably, he would be able to gather about 6 or 7 times the amount of light, much quicker than I would be able to with a 10-inch, for instance. Okay, does that answer your question? So, and there are some things, now that I think about it, as far as photography goes, there are certain things that you don't have to worry about also. So if you want to take pictures of the moon, or for that matter, if you want to take pictures of planets, normally you're taking videos and they're very short exposures, or the sun, for instance. You only need very short exposures, so the field rotation is not so much of an issue. And okay, and we're going to talk a little bit more about mounts next week. with the hands-on demo. Would anybody like to see, well, I'm going to go, I think we have already talked about this. Equatorial, the right ascension, is paired with the perpendicular axis declination. As I said, we move this and we are moving it in right ascension. Likewise, we move this, we're moving it in declination, and note the two axes are perpendicular to each other. You can't, most of these, I can't even get a motor for this mount, but however, I consider it a mount that I use more so for teaching than anything else. So as a result, the motor really isn't an issue for this scope. And the image will not rotate in the field of view, as is the case with the out-as mounts, such as the previous question. Okay. The manual mounts usually have setting circles. And we'll talk about those in the next chart. Okay, you see right here, up here we have things that are graduated 16, 17, 18, 19, 20. Those are aligned with the essentially the sidereal day, which is 23 hours, 56 minutes, 9 seconds, and a little bit of change. Okay, and if you want to know why do they have two numbers, one on the top, the bottom number is normally for the northern hemisphere and the top number is for the southern hemisphere. So you can switch back and forth. And likewise, the deck axis is divided up into degrees, 0, 10, 20, 30, 40, 50, etc. So up through 360 degrees, well, 180 degrees on each side. Okay, have I said anything else? Essentially, with this, such as this scope right here, just a brief explanation. We will try to cover it in more detail next week. If we are polar aligned, for instance, all we have to do, first thing you're going to do, let's say we're polar aligned and we know the declination of a given object. So we switch the declination to whatever it would be. And at that point, since our declination is set, all you have to do is take the right ascension axis and it should come into the field of view. When it comes into the field of view, then there's another little knob down here that's actually movable, but you can set the right ascension setting there. And as a result, and subsequently, all you have to do is turn this, turn the right ascension axis and you will track. So, which is essentially the same thing that a motor does. That was a very brief explanation, and it's not quite so easy in reality, but however, I will try to do a better explanation of it later. Go-to scopes are popular. My own opinion, well, I think I'm going to talk about that in the next chart, so I'm not going to say my opinion right now. Okay. I talked about a meridian flip, okay, such as you need to do a meridian flip with a German equatorial mount. The meridian is a line, if you look straight to the north, which I think that's probably in, no, which way would be the north? North. Okay, if we look straight to the north, okay, and we draw a line directly overhead that ends directly to the south, that is the meridian. Okay. With a German equatorial mount, this isn't the case with this thing because it's just a manual mount, but however, when the axis nears the limit when the scope is pointing near the meridian. Okay, and a maneuver is required to switch the right ascension and the deck axis. Some software will automatically perform a meridian flip. And this is probably all Greek to everybody here, but over the next chart, I am going to try to illustrate what it is. If we start out on the left-hand side, we are currently tracking east of the meridian. Okay, and this is a go-to scope, go-to mount. It's a Celestron AVX, which I like to call the Toyota Camry of equatorial mounts because it's very reliable, it's easy to use, and very friendly, and does a great job overall. But however, we know rotation is coming around this way as this changes the right ascension axis. And when the axis gets parallel to this point, your scope is actually pointing to the meridian. In other words, it is pointing to the meridian, that line that I talked about that goes from the north the whole way over to the south. And all of your go-to mounts will have an RA limit that is settable. I usually set mine to about 15 degrees, but I've never really gone before that. We do have a few German equatorial mounts that will go quite a bit beyond that RA limit, but however, the only ones I know of are astrophysics, and if you have $16,000 or $20,000, you can buy one. So this mount itself is probably about $900. Okay, so what happens? Okay, right here, you're just about pointing at the meridian, and that is a warning, turn it the other way, okay, because you're going to be approaching the limit at that point, because you're going to continue, rotation is going to go, and eventually it's going to stop altogether. And I have never heard of any damage done to a mount as a result of going past the RA limit, but nonetheless, many astronomers worry about that. So as a result, what has to happen, such as for instance, we were pointing this way, okay, and right there, we would be pointing at the meridian essentially. Okay, and that would be the limit that we can go to. And so what happens, you have to do something called a meridian flip, which essentially flips the right ascension axis, and then this will continue to track. Okay, it takes, even on a go-to mount, like I said, some of the software will do a meridian flip automatically. I normally do mine manually. Okay, and likewise, over here, we have the meridian, we have the rotation, so you can track the rest of the night on your target if necessary. Okay, does that clarify what a meridian flip does? Okay, I promise you. Normally, it's probably more of a concern for astrophotography than anything else. But however, if you have a scope such as for, let's say I'm in an outreach event, okay, and I'm doing nothing but visual astronomy, but however, I'm just tracking on something, I still want to do the meridian flip, for the big reason I don't want to reach the right ascension limit. Okay, now what else? I have some suggestions for the beginning. I didn't get the joke. Oh, okay, okay. Well, what we talked about a little bit later, just Dr. Bickle and I. If I go to somebody who knows something about scopes before you buy one, but however, before that, attend multiple DAS open houses. There will be lots of scopes there. There will be lots of examples. There may be binoculars. There will be alt-as. There will be Dobsonians. And if you guys want, I'll set this one up next week too. So, and do a little bit more of a demonstration on how to steer here and there. Okay, but no, I would not buy a Walmart scope for $100. You can, if you multiply that even by a little bit of a factor, say, I don't know how much a inexpensive Dobsonian would be, but probably for $300 you could probably get a decent Dobsonian. So, alt-as spotting scopes. To start out with the small Dobsonian or binoculars. This is my own device. A lot of people will probably not agree with me. I consider a manual gem after some experience, and you will learn lots. And the reason that I say this is because I think I've told a couple other people when I was probably 11 or 12 years old, I worked 2 summers, I think, and I saved up $100 so I could buy a Sears Roebuck 2-inch refractor. And it was a German equatorial mount. And as a result of that, I learned all about these setting circles. I learned about what is happening in the sky, how everything is moving, what sidereal time was, and the local sidereal time, how to find out what it is, etc. And that's one of the reasons why I sort of recommend, although I don't know that anybody has ever taken my advice. So, and if you end up being confused about something, I know even a lot of times I talk to people about astronomy and they confuse me. Talk to somebody who doesn't confuse you, okay? And just remember one thing, for instance, my preferences and ambitions have changed probably 5 or 6 times, and I end up buying equipment to correspond with that, but however, a lot of times I still end up going back to one of those things that I've done previously. So all equipment just about all my equipment is used for one reason or another. Okay, a little bit of suggested reading. Starware, the Amateur Astronomer's Guide to Choosing, Buying, and Using Telescopes and Accessories. Excuse me. Navigating the Night Sky, it's part of the Patrick Moore Practical Astronomy series. I probably have probably somewhere between 10 and 15 books that are Patrick Moore Practical Astronomy series. A lot of great information in that series. Facts from Space, just a lot of fun things about stars, nebula, galaxies, telescopes, etc., etc. One of my favorite books, which is all about stars, written at a very, very basic level. If you're interested in stars, which I happen to be probably interested in stars more so than I am anything else. The Secret Lives of Stars by Lisa Harvey Smith. Easy to read, it's funny, has a lot of humor in it, and a lot of great information. Any astronomical atlas will do. And any additional questions, please contact me, and that's my email address, which I guess now I'm putting it into the public domain. Okay. Okay, what's your question, Dina?
Oh, I didn't know. Can you make this slide deck available for the people in the class? Can it be emailed out as a PowerPoint to people so they have it for reference?
This is going to be available for everybody in this room.
Okay, good.
It is going to be available. And I think that sequentially, as they are done, they're going to be available for anybody in DAS or the Secular Hub for that matter. Okay, but however,
It'll be on a YouTube channel, and you'll get the link in an email if you're registered for this event.
I think we talked last night that it wasn't going to be made available to the general public until all 6 or 7 modules were ready.
Right. Of course, you can share the link. I didn't say that.
Okay. Okay, any other questions about, well, no, not done yet. So I'm sure that everybody's wanting to get out of here. No. Okay, any questions about DAS, astronomy, telescopes, or DAS membership? If you're interested in anything that I talked about, please join Denver Astronomical Society. Yes?
Can we just verify the address we're going to next week? I've got. I just want to verify what address we're going to next week.
Look for Observatory Park in Denver, and you'll find it.
Look for the dome, and then just go south of that.
We have a question way back here.
Yeah, I wondered if you could talk a little bit about the DAS loaner program.
The DA, I'm not altogether sure that I am all that qualified to talk about the DAS loaner program. It's available to any of the DAS members. Okay, not to the general public. Okay, and often we do get requests from the general public, and we say, hey, join DAS, it's that simple. So, and so are you a DAS member? Okay, you're home free. I'm not sure of what all is available there, though. If we had one of our quartermasters here, they could tell, but normally, Dina, do we have Dobsonians generally that we rent out?
I think we have 4 or 5 Dobsonian telescopes.
Okay.
The beginner level telescopes.
Yeah.
We don't usually rent out the more advanced telescopes unless you're an experienced observer.
Okay.
And you have to give us a deposit when you borrow a telescope, but usually we just hold your check and give it back to you when you turn the scope back in. The period of the loan is 30 days.
Okay. Okay, and I'm going to ask this question again. Who plans to attend the hands-on meeting next week at Chamberlain? Oh, wow, are we going to have fun? Okay, is anybody bringing mounts with them?
Will the weather change that?
The weather would change that, yes. Okay, as we may, if the weather is bad because of snow, rain, or intense cloud cover, or a tornado goes through, we'll probably we may end up rescheduling it until after the last meeting, okay, which would stretch it out probably into the first part of May.
What is parking like?
Along the road. Yeah, you can. You are around Observatory Park there. I think you can park around two of the roads around Observatory Park, which would probably, I don't know, probably fit 30 cars. And then I think on the other side of Iliff, you can park on that side too. So we should, it might be tight, but we should have enough room for everybody.
Yeah, all close to the car in front and behind you, like what we do on Main Street. Yeah, that helps sort of consolidate, or can we carpool?
Yeah, you can, yeah, that'd be great if people would carpool. Always a great idea to carpool. Okay, and I'm sorry, one thing I will apologize for is that probably everybody here came to talk about astronomy, and I didn't talk much about astronomy tonight, did I? To tell you the truth, if I would have had my choice, I would have rather talked about astronomy. Okay, but anyway, you can hire me for something else. Okay, a couple of the things, I like these little sayings. That this one's by Doug Adams. There is a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened. And I can verify that because Edwin Hubble in 1917 said the great spirals, galaxies, they used to just call them spiral nebula. They didn't know they were collections of stars. And he said the great spirals with their enormous radial velocities and insensible proper motions apparently lie outside our system. In other words, outside our galaxy. And that indeed turned out to be true. And after that, we have even another chapter where not only do we have all these galaxies, but we have a multiverse that we've come up with. So anyway, that has been replaced several times. So Douglas Adams is right after all. Okay, anything in closing?
Thanks,
Okay.
Steve.
Thank you.